In this video, you are going to learn about the development of quantum theory. In particular, you are going to learn about the quantum numbers to describe an electron in an atom. As we have seen the Bohr model before, if I have a positive in the inside nucleus, then surrounding it, there can be an electron over here. If I have another positive, with this electron itself is fine. But if I put another electron in the same time, because this electron is going to repel with this electron, so they cannot be freely running in a circular path. In this case, this Bohr model, it doesn't work. It doesn't work. So there will be a new model, it's called a quantum mechanical model. Okay, so the quantum mechanical model, it is a description of finding the probability of finding an electron. Okay, that means we can see where the electron can go if we know the probability. Let's say if this is the nucleus, if the probability goes like this, that means only in this region I can find the electrons. Not everywhere, not going in the circular path. Okay, so let's look at this one. As for now, I'm just going to give you those numbers. Okay, the derivation is very complicated, but we come out to be, there are 4 numbers. The first one is n. N is called the principal quantum number. Okay, and as you have seen before, this n is the same n as the one showing in the Bohr model. Okay, so this is the first quantum number. What is the second quantum number? And it is the L. So this one is called angular momentum. Okay, the next quantum number will be ML. This is the magnetic number. Magnetic quantum number. The last one will be the spin. It's called MS. This one is the spin. Okay, so what are the allowable number? Still, it looks very complicated now. Okay, so when n is equal to a certain number, the L, n can be the first principal, second, and 3, and on. But the L can only start from 0, 1, and on until the number is n minus 1. Okay, we are going to do some exercise. All right, so for example, if n is equal to 1, what are the allowable L? It would be start from 0, and if n equal to 1, can it be 1? No, because the highest number is n minus 1. Okay, so you have to write this down. You may have to go back and forth in this video because I will cover a lot of material. All right, the magnetic number. Magnetic number will have the form, it will be from minus L plus 1 all the way up to positive L. Okay, so let's say if L is equal to 2, so what are the allowable ML number, the magnetic number? It will be minus 2 because it starts from minus L all the way to L, all the way to 2, and we just have to fill the rest in. Minus 2, minus 1, and then 0, and then 1 and 2. Okay. As for the spin number, we only allow that to have either a positive half or a negative half. All right, so these 4 are called the quantum numbers Okay, so let's get started. You may need to memorize this for a while, at least for 5 minutes. Okay, let's look at this way. When n is equal to 1, okay, what are the possible L? Because L is from 0, 1, 2, until n minus 1. So 0 is the only number. When n equal to 1, so L, so this is a possible L. L equal to 0, okay? So when n is equal to 2, what are the possible ones? So L, it can be 0 or it can be 1. How do I know that? Because I will start from 0 and I go all the way to n minus 1. If n is equal to 3, what are the possible L? It will be from 0, 1, and 2. If n is equal to 4, what are the possible number? It will be 0, 1, 2, and 3. Okay? All right. So what is the next number? So this one is called the angular momentum. The next number is called the magnetic number, magnetic quantum number. And magnetic quantum number, what you can have is from minus L to L. In this case, minus L is 0, L is 0. So the only allowable number will be 0. Okay? When this one, when n equal to 2, L equal to 0, what are the possible numbers of ML? Just 0. Okay? How about here? When n equal to 2 and L equal to 1, the possible number will be minus L, minus 1, all the way to L, all the way to 1, and in between, this is 0. I can do the same thing. I can do over here. 0, I can only have 0. 1, I can have negative 1, 0, and positive 1. And 2, I can have minus 2, minus 1, 0, 1, and 2. I can do the same thing if it is 3. See, when n equal to 4, I'm allowed to have L equal to 3, and the possible number for the ML will be minus 3, minus 2, minus 1, 0, 1, 2, and 3. So those are the allowable quantum numbers. And if you look at the last one, the spin, no matter where you go, you can either have a negative half or a positive half, always. So what do these quantum number have to do with the energy? Okay, let's look at this way. When L is equal to 0, when L is equal to 0, we can call this as an s orbital. Okay? When L is equal to 0, we can call it s orbital. When L is equal to 1, we can call that p orbital. When L is equal to 2, we call that a d orbital. When L is equal to 3, we call that f orbital. Let's see. When n equal to 1, I can only have s orbital because I only have the 0 over here. When n equal to 2, so this is s orbital. When n equal to 2, I can have s orbital and I can have p orbital. When s equal to 3, I can have s orbital, p orbital, and d orbital. When n is equal to 4, I can have s, p, d, and over here, L equal to 3, I have f orbital. Okay, so that's how we create that energy chart. All right, so for the s orbital, how many lines can I have? I only see one number here. That's why I only have one line. for me to fill up the electron. So over here, I can see one line over here. Over here, the 2p, I should have 3 lines. Over here, 3s, 1 line, 3p, 3 lines, and 3d, I should have 5 lines because I have 5 numbers. Okay, and for the F, I have 1, 2, 3, 4, 5, 6, 7. So I have 7 lines for the F. 1, 2, 3, 4, 5, 6, 7. Okay, so that is exactly how we get this electron chart over here, the energy chart over here. So when it is S, over here, S, one is 1s, that means n equal to 1, I only allow that n equal to 1, I only allow to have s orbital. When n equal to 2, I can have s and p. When n equal to 3, I can have s, p, and d. That's where we find it. And how come here in the 2p we can have 3 lines? Well, that is based on what we have. Where did it go? Okay, that is from where we got it from before. Okay, that's from here. All right, and those lines, so the last one is the Pauli's exclusion principle. That means on each line, you can either have up or down. So up means positive half and down means negative half. That means for each electron, we can define it by these 4 quantum numbers. And none of the electrons will have the same 4 quantum numbers. When you come back to this one, let's look at this. When n equal to 1, n equal to 2, over here, when n equal to 2, what happened? It's not on the same line. See, 2s is lower than 2p. That means, you have to remember this, the energy would depend on, the first thing is, what principal level it is. Okay, see, 1s is different from 2s. The second thing is the angular momentum. That means even if it is the same n, okay, even if it's the same principal energy level, in this case, it's equal to 2, but 2s and 2p is different. That means it also depends on the angular momentum L. And that's it, and nothing else. See, because the electron over here, we have the same energy as the electron over here. So it doesn't depend on the ML. The ML shows which one it is. And over here, pointing up and pointing down, it has the same energy level. So it's independent of the MS.